Okay, this is my chapter 13 video presentation. So, chapter 13, and it's problem 13.5.1. And now we're going to start with part A. Okay, so for part A, the New Horizons spacecraft, mass 478 kilograms, was launched from Earth in 2006 and flew past Pluto in 2015. What minimum amount of work has to be done on spacecrafts of this mass to send it from the Earth's surface to infinitely far away from the Earth? Neglect air resistance and the gravitational effect of the Sun, Moon, and other planets. Express your answer with the appropriate units. Okay, so we're going to use equation 13.9 in section 13.3. And so equation 13.9 and section 13.3, and that is W grav equals V1 minus V2. And then solving this more, W equals negative over G M over D minus G M over D. Oh, lowercase d. Lowercase d. Right? And so the work W done by the gravitational force is given. So we know that is G equals G minus G7 4 over 10 or negative 11. M3 over KG2. Now this is a gravitational constant. So now we're going to list the mass of the Earth, the mass of the spacecraft, and and the distance from the center of the Earth to its surface, and the distance between the Earth and Pluto. So we're just going to list those out real quick, just to kind of see what we're doing. So M equals 5.972 over 10 negative 2. This is the mass of the Earth. So that's the mass of the Earth. And this is M equals 478. And this is the mass of the spacecraft. This was given to us, by the way. This is the mass of the spacecraft. So mass of S, and then mass of E. So now we're gonna do D equals, which is the distance. So D equals 6,371,10 over 3 meters. This is the distance from the center of the Earth to its surface. So so that's the distance from the center of the distance from the center of the Earth to its surface for D. And then for capital D is 7.529 over 10 over 12 meters. And then this is the distance between the Earth and Pluto. Yeah, this is the distance between Earth and Pluto. So by rearranging everything, we will get W equals G. Well, we're going to rearrange this right here. Rearranging this right here, we get W M over 1 over lowercase d plus 1 over capital D times 2. So basically, we're just going to plug everything in. So W equals 6.674 over 10 negative 11 M3 over MGS squared. And then multiply that by 5.972 over 10 for 10 1024 kilograms. And then this is the mass of the spacecraft, which is 478 kilograms. Basically, we're just doing this. We already have our values. We're just listing it in here and plugging it in. And then, so solving this, we should get 1 over 6, 471 10 negative 11. Okay, yeah, so solving this, oh yeah, and then times 2. So then solving this, we'll get our answer. W equals 2.99 10 times 10 to the 10th joules. So basically, to recap on what we just did for part A, we used equation 13.9 in section 13.3, so this right here. Then we just listed out the values, and then we rearranged this right here. So so G, capital M, M, then 1 over D plus 1 over D times 2. So yeah, and then we did that and solved. Actually, I think I messed up on this one. I'm just gonna redo this one again. So so 6.674 times 10 to negative 4 times 5.972 times 10 to the squared. Put this in parentheses so we don't get confused. Times 478, which is the mass of the spacecraft. And then over 1 over 6.371 10 times 10 to the 10 to the third. And then we multiply that again and get 1. We add that. My bad, not multiply. We add this, and then we get 1 over 1 over yes, 1 over 7.529 times 10 to the 12th. This is just we're adding this, and then that gets our answer. W equals 2.99 times 10. So I kind of made a mistake real quick. I wasn't really looking at this right here. I was just solving it. I forgot to add the 1 right here. So yeah, so basically we just plugged this in and solved it, and we get the answer right here. So now for part B. So for part B, a piece of spacecraft debris initially at rest falls to the Earth's surface from a height above the Earth equation. Oh, let me read that. A piece of spacecraft debris initially at rest falls to the Earth's surface from a height above the Earth equal to 1/2 of the Earth's radius. Find the speed at which the piece of the debris hits the surface. Neglect air resistance and gravitational pull of the moon. Okay. So we're going to apply the energy conservation. We're going to apply the energy conservation law in example 13.5 in section 13.3. So that law is like this: 1 over 2m times 0 t plus negative gm em over r plus h. And now and then simplifying some more, that would equal to be 1/2 mv2 minus g em over r. Now we plug in our values that we got from our previous part A that we listed out there. So we know this is negative g 0.673. Remember, it was negative 6.73 times 10 to negative 11 times 6 times 10 to the 24. 6 times 6 to the 24th. Oh, 6 times 10 to the 24th, yeah. So then in the bottom, which is R, is 6.371 plus 6.371 over 2 times 10 to the third. And then solving this will equal 1/2 V2 minus 6.673 times 10 to the negative 11 times 6 times 10 to the 24th over 6371. And basically what I'm doing is I'm just simplifying the equation. So negative 6.6, so negative 673 times 10 to the negative 11 times 6 times 10 to the 24th, and then 6,371 plus 3, which is 83.5 times 10 to the 3, and then that would equal to be 1/2 v squared, and then solving this, that should give us our answer, which is V equals 6460. V equals 6460 milliseconds. So basically, we use the energy conservation law, which was shown in example 13.5. This whole problem was basically in example 13.5. I basically kind of used it to solve it for the homework and saw how they used it. And they used the energy conservation law and plugged everything that they got from the previous problem right here into this right here. And yeah, and substituted and solved and simplified it and solved. Now for part C. For part C, an astronaut on Mars, mass 6.42 times 1023 kilograms, radius 3.39 times 10 to the 6 meters, launches a probe straight upward from the surface at 3 times 10 to the cube milliseconds. What is the maximum height above the surface that the probe reaches? Neglect air resistance and the gravitational pull of the 2 moons of Mars. Okay, so we're going to use the energy conservation principle. And the energy conservation principle. And also energy conservation principle. Yeah, we're going to use the energy conservation principle. And this would be K EI plus UI equals K EF plus UF. This is a equation. Yeah. Okay. Yeah. This is the energy conservation principle. Okay. And then we're gonna use equation 13.5, which is 1/2 mv squared plus negative g g capital M lowercase m over r equals 0 plus negative g m, and then r plus h max. And also this equation was displayed in 13.5, which is like similar in part B. So now we set things up. So now V2 over 2 equals Gm times 1 over R minus 1 over R plus H max. And then now we just plug in our values. So we know that 3 times 10 cube, which is the probe straight upward from the surface. So, and then put that over 2, and then 2, and then this will equal GM. So GM is GM is like somewhere up here. So 6.673 times 10 and negative 11 times 6.42 times 1023. Now, mind you, the 6.42 I got from the mass, an astronaut on Mars. That's the mass of the astronaut on Mars. And then, yeah. And then times this by 1 over 3.39. This is the radius times 10 to the 6. 10 to the 6 minus 1 over 3.39 times 10 to the 6 plus H max. And then solving all of this, we will get our answer 1.87 times 10 to the 6 meters, and that'll be your answer for part C. So basically, we use the energy conservation principle, then the equation 13.5, an example 13.5. Then we plugged everything in, and then yeah, we plugged it. No, not this was used in this is equation 13.5 in section 13.5. My bad. And then we plugged everything in, and then we plugged it, and then we solved it, and yeah. So a lot of these problems right here is from part A. So it's like all like, continuous from part A to part B to part C. So it wasn't really much for me to really do except for just look at part A and then see what values that they had, and then kind of just use the equations accordingly to the problem that they gave me, and plug it in using the values that we got from part A and the answers that we got from part A, some of them. So then part A, so A, B, C, D. So for part D, which is the last one, because this part had, this was 13.5 into A, B, C, D. So the last one, part D. Okay. So in order to rendezvous with an asteroid passing close to the Earth, a spacecraft must be moving at 8.50 times 10 to the cube milliseconds relative to the Earth at a distance of 2.50 times 10 to the 8 from the center of the Earth. At what speed must this spacecraft be launched from the Earth's surface? Neglect air resistance and the gravitational pull of the moon. Okay, so from the center of Earth, then by the conservation of energy, we have 1/2 mvi2 equals 1/2 mvf2 plus gm ds over 8.2 equals 1/2 mv f2 plus g capital M lowercase m, and this is 1 over radius, it's 1 over lowercase m minus 1. Okay, so this is where m is the mass of the ship, g is the gravitational constant, m is the mass of Earth, r is the radius of Earth, and yeah, and r with the capital R is the radius of Earth, and lowercase r is the distance from the center of Earth, where the spacecraft is moving at a final speed. So basically, we're going to use equation 1, which was up here. I was labeled this as equation 1, so we don't get lost. So okay, so yeah, so Wi equals VF2 plus 2GM over 1 over capital, which is, this is the radius, this is a radius Earth in distance from the center of the Earth, so minus 1 over lowercase r, which is the distance from the center of the Earth, and then parentheses 1 over 1, okay, yeah, 1/2. Okay, so now we're going to substitute the values given to us. So we know that VF equals 8.5 milliseconds, and we know G equals 6.674 times 10 to the negative 11th. Then we know capital M equals 5.972 times 10 to the 24th kilograms. And capital R equals 6.6378 times 10 to the 6th meters. And then we know lowercase r equals 10.5 times 10 to the 8 meters. So then now we just plug in for those, and so let's plug it in. So yeah, so 2 times 6.674 times 10 to the negative 11th times 5.972 times 10 to the 24th kilograms, and then we're gonna have to kind of like go on this line right here, kilograms. So we're just gonna go to the next line. So 1 over capital R, which is 6.6378 times 10 to the 6 meters, minus 1 over R, which is R is 2.5 times 10 to the 8th meters. Make this a little bit neater. Meters. And then over 1/2. So yeah, so over 1/2. Let me sure I did this right though. Over 1/2. Okay, yeah. So, okay, yeah, that's right. So solving this will give it our answer, which is V1 equals 1.39 times 10 to the 4th milliseconds. So basically, this is my video presentation for chapter 13, which is 13.5.1, which is the first problem. And a lot of these problems you would have to solve part A to even solve part B, C, and D. And I referenced the equations. I took examples from the book and referenced the sections. And yeah, I got the answers and I plugged it in and solved it. And I think that's about all it is. It was only parts A, B, C, D, so it was pretty short.